Hello students and welcome to my channel Maths Hub by Dr. Tanya. So in my previous videos I have been teaching you about lattice, and in my last video I talked about the least upper bound and the greatest lower bound. So let's do in this video what is basically a lattice. So let us come to the definition, and with the help of examples I'll explain how to check whether a given poset is a lattice or not. So let's come to the definition of a lattice. A lattice is a partially ordered set, and any partially ordered set is given by the symbol L and less than equal to, in which every pair of elements has a least upper bound and a greatest lower bound belonging to L. That means in any poset L with less than equal to sign, if every pair of elements, you take any two elements in that poset, if it has the least upper bound and a greatest lower bound, then it will be called a lattice. So let's recall what was the least upper bound and the greatest lower bound. So the least upper bound was, if you remember my last video, I told you that it is also called as supremum or LUB. So that means if I am taking two elements A and B belonging to the poset L, then the supremum or the least upper bound are denoted by these symbols. So you can give this notation A plus B. You can give the notation A join B. It is also meaning the same as A union B or A plus B. So least upper bound will be denoted by the symbol. It will be denoted by the symbol this, which is called as join, and we will be calling throughout in this chapter as join or the sum of A and B. Now let us recall what is the greatest lower bound. The greatest lower bound, it is defined as the infimum or the GLB. So that means if I have two elements A and B belonging to L, we can denote the infimum or the greatest lower bound by the symbols A star B or A meet B, or it is also equivalent in saying A intersection B or A dot. So here this symbol, opposite of victory symbol, will be called as the meet symbol or the product of A and B. So in nutshell, if we have any two elements A and B belonging to L, if A join B and A meet B both belongs to L, then that poset will be called as a lattice, right? So let's check with the help of certain examples that whether the given posets will work as lattice or not, right? Now before we move on to checking whether they are lattice or not, let's see these remarks. Now the meet and the join, they are the binary operations on a lattice, since LUB and GLB of any subsets of a poset are always unique. So I told you about this remark in my previous video also, that whenever we will calculate LUB and GLB, if they exist, they are always unique in nature. Unique means it will always be one. There will be never two GLBs or two LUBs, right? And the second remark says that all posets are not lattices, but for lattice it should be a poset, right? Because in the definition of lattice, we are saying that any poset. So every lattice is going to be a poset, but it is not necessary that every poset is going to be a lattice. We'll come across many examples where you will see that some of the posets are not lattice, but some are acting as lattice, right? So now let's move on to the first example and let's see whether it is a poset or not. So we have the set L equal to 1, 2, 3, 5 and 30 under the divisibility relation, and we need to check whether it forms a lattice or not. Now for lattice, how do we check for a lattice? We will make an operation table for join operator and we will make a table for the meet operator, right? So I'll explain you how to prepare the join table and the meet table. So this is how we are going to make the table, and we are going to write the entries of the set L, all the elements in the rows as well as in the columns. So the elements of L are 1, 2, 3, 5 and 30. So we will put the elements in the rows and similarly we will put the elements in the columns, right? So we have the second element as 2, then we have 3, then we have 5 and then we have 30. Now, if you recall my last video, I told you that whenever the relation is divisibility, then what is the meaning of join and what is the meaning of meet? Join means that you have to calculate the least upper bound. So least upper bound means we have to calculate the LCM between the two elements A and B. And whenever we talk about meet, meet means that we are talking about the greatest lower bound, and it is called the HCF of the two elements, that is A and B. So now the first table that we will construct is the join table. So when it is a join table, you'll put the symbol of join here, right? Now let us come to each of these cells. Now the first cell means 1 join 1. And what is the meaning of join? It means the LCM of the two elements. So what is the LCM of 1 and 1? It is 1 itself, right? Then 1 join 2, the LCM is 2. 1 join 3, the LCM is 3. 1 join 5, the LCM is 5. 1 join 30, the LCM is 30. So whatever entries we have got in the first row, we will fill the same entries in the first column also, right? You will find the same elements are there. So you do not have to apply the operation again. You can write the entries there. Now let's come to the next cell. This cell refers to 2 join 2. So the LCM of 2 join 2 is 2. Next, 2 join 3. The LCM is 6. 2 join 5. The LCM is 10. 2 join 30. The LCM is 30. Right? Let's fill the entries in the second column. 2, 2, 6, 10 and 30. Next, 3 join 3. The LCM is 3. 3 join 5. The LCM is 15. 3 join 30. The LCM is 30. Let's fill up it here. We get 15 and 30 over here. Next, 5 join 5. The LCM is 5. 5 join 30. The LCM is 30. Now let's fill 30 over here. And the last cell refers to 30 join 30. And we get the LCM as 30. Right? Now, after you have completed the join table, whatever entries you are getting over here, check whether all these elements they belong to set L or not. So if you look at all the entries, you can see that there is a 6 here, there is a 10 here, and there is 15 here, which do not belong to this set L, right? So in the definition of lattice, we said that A join B should belong to L. So you can see that here 2 join 3 is equal to 6 and it does not belongs to L, right? So we have here 2 join 3 is equal to 6, but it does not belongs to L. So we will declare this as it is not a lattice, right? Because these entries are not belonging to set L, right? Now suppose if all these entries were belonging to set L, then what we will do? Then we will go on to the meet table. Otherwise, we will declare it here that 2 join 3 is equal to 6, which does not belongs to L. And hence, this L is not a lattice. So this is not a lattice. Right? So I hope this is clear. Right? So let's move on to the next example. So here you don't have to construct the meet table, but I have given you the meet table so that when you can draw it, you can understand how to construct it. So when we are making the meet table, the only difference is we will write the same entries in the rows and columns and we will put the operator here as meet. And now meet means to calculate the HCF between the two elements, right? So when we are calculating the HCF between the two elements, like meet 1, I'll just show you the table so it will become more clear to you. Yeah, so this is the meet table. So you can see here 1 meet 1 is 1 means HCF for 1 and 1 is 1. 1 meet 2 is 1 again because the HCF for 1 and 2 is 1. 1 meet 3 is 1. 1 meet 5 is 1. 1 meet 30 is 1. So you can see that I've completed the entire table, but all the elements are belonging to L. But In the join table, the elements were not belonging, and so we can declare from the join table that L is not a lattice, right? So to completely declare that the poset is a lattice, the join table entries and the meet table entries all should belong to set L, right? Okay, let's do another exercise and let's see that whether it is a lattice or not. So this is the power set of X, where X contains the elements 1 and 2. So the power set contains the elements 5, singleton set 1, singleton set 2, and the complete set 1, 2. So if you remember my videos, we have done this exercise there. And if I draw the haze diagram looks like this. 5 is here. 1 and 2, they are at the same levels. So you can try the haze diagram on your own. So you can join them. And finally, we have 1, 2 over here, right? So let's join this. And this completes your haze table, right? So let's see the join table. Now, if you remember in my last video, I also said a shortcut to calculate the LUP and the GLB. While you are calculating the LUP, the least upper bound, you have to go in the upward direction, and whoever is the first point of contact, that becomes your LUP. And whenever you are calculating the GLB, it is the lower bound, so you have to go in the downward direction, and the first point of contact in the downward direction will give you the GLB. So the join operator is written here. All the elements of the set are written in the rows as well as in the columns, right? Now, phi join phi. Phi join phi is always phi because it's the same element, right? And let's see what is phi join 1. Now this is phi element here and this is 1 element here. So phi join 1, since we are talking about join operator, and join operator means the least upper bound. So we have to go in the upward direction and the first point of contact. So you can see that phi and 1, the first point of contact is 1. So our answer is 1 here. Then phi join 2. Phi and 2, the first point of contact is 2. Phi and 1, 2, who is the first point of contact? It is 1, 2, right? So we get the elements 1, 2 here, and we pull in the same entries in the first column, right? Now the next entry is 1 join 1. 1 join 1 is again the same element. Next is 1 join 1, 2. Now 1 and 1, 2. Who is the first point of contact? It is 1, 2, right? Then similarly 1 and 1, 2 is again 1, 2. Next, so we put in the entries again here. Next entry is 2 and 2. So same element 2. Now 2 join 1, 2. So who joins 2 and 1, 2? The first point of contact is 1, 2. So we fill that entry over here also. And then 1, 2 and 1, 2 is again the same element 1, 2. Now if you look at this table, you can see that all the entries, whatever entries we are getting in the join table, they all belong to E, right? So the join table is perfectly fine. So now let's go on to the meet table. So we'll construct the meet table, and meet means to calculate the GLB. So GLB means that we have to go in the downward direction and we need to select the first point of contact. So phi meet phi is phi, it's the same element. Phi meet 1. So phi and 1, who is the first point of contact in the downward direction now? So it becomes phi. Phi and 2, the first point of contact is phi. Phi and 1, 2, again the first point of contact is phi. So we write the same entries in the first column also. Now the next entry is 1 and 1. 1 and 1 is 1. 1 and 2. Who joins 1 and 2 in the downward direction, and who is the first point of contact? It is phi. So we write down phi here. And then we have 1 and 1, 2. 1 and 1, 2, the first point of contact is 1. Right? So we pull in the entries here also. Then the next is 2 and 2. So 2 and 2 will be the same element. 2 with 1, 2. 2 and 1, 2, the first point of contact is 2. And likewise, when we complete the entire table, we can see that all the elements that we are getting in the meet table, they all belong to the set Px. So that means Any two elements you pick in Px, the join as well as the meet, they all belong to Px. So we can declare that Px is a lattice. Right? Let's move on to the next exercise and see whether it is a lattice or not. So this is the Hayes diagram given to us, and we need to check whether it forms a lattice or not, right? So I'm not going to explain the entire table. I'll just focus on two particular elements. So let's see B and C. What is B join C? Now B is here and C is here, right? I have to calculate the first point of contact in the upward direction. So in the upward direction, the first point of contact is B this side and it is E this side. But we know that the least upper bound is always unique. There cannot be two LUPs. So in this case, B join C will not exist and it will be equal to 5. Right? So we cannot say that B join C is D or E. They are upper bounds, but they are not the least upper bound because both are at the same. They are at the same level, right? So we cannot declare that D is greater than E or E is greater than D. So we will say that B join C is equal to 5. So this element becomes 5 and similarly this element is also 5. Rest of the elements, when you calculate the join operator, they will all belong to this lattice, this poset, right? So, but since these two elements are coming out to be 5, so we can say that B join C is equal to 5, which does not belongs to this structure L or the poset L. So L is not a lattice, right? So you do not have to calculate the mean. If the join table is perfectly okay, then you move on to the meet table and check the meet operator. But if the join table is giving you some problematic issues, so you can declare it that it is not a right. So with the help of these examples, I think that you can perfectly check now whether a given poset is a lattice or not. And few more examples are given in this video. So the solutions are also given there, so you can check it out. And please tell me in the comment section if there is any doubts regarding any of these exercises. So I'll give you the solution and I can also explain it again. So you can try these exercises and you can check whether they are the posets or not, right? Without looking at the answers are already given in the video, right? Many examples are given here for your practice. You can try all these exercises. So this is one more exercise. We have done this Hayes diagram also in my previous videos. So you can check whether it is a lattice or not. And that's all. Thank you for watching it and please subscribe my channel so that you get an update. Believe in yourself and you will be able to succeed. Thank you so much.